a warm welcome to Mr. Daniel Raravi. Mr. Raravi is the Director of Marketing and Strategic Initiative at Mastercam India. Coming with an engineering background, Mr. Daniel is a tool and die alum from a Government Toolroom and Training Centre.
But what I'll try to do is, give the philosophical perspective of high-speed machining, the result of the influences of various factors in high-speed machining. High-speed machining, advanced manufacturing, high-efficiency machining. All these are terms that we've seen come up in the last 20, 30 years. There's a reason why it has happened so. One is because of the technological advancements that have been a part of a number of machine tool organizations, cutting tool evolutions, the computing capability, which gives rise to a number of strategies, faster computing for CAM softwares, the innovations in materials technology, the innovations in coating, the innovation in tooling balance, and how vastly you could make sure that the spindle runout is reduced, how we are able to reduce machine tool vibrations, how we are able to achieve thermal stability while machining. All of these are some of the factors because of which we are discussing this topic called high-speed machining today. The evolution of this starts with the core principles and followed by the innovations and where this technology is going to take us forward in the future. So let me just start off. Obviously, they say necessity is the mother of invention, and therefore HSM also is a process that has come about because of the rising demand for profitability. I think when Mr. Menon spoke, he spoke about one very important characteristic called the high material removal rate. Now, why high material removal rate? So if I were to equate it with a human being, let's say, for example, if I'm walking from my home to my workplace, and it takes me at a very decent walking pace, about 15 minutes. What is the need for me to reach my workplace in less than 3 minutes or in less than 5 minutes? That is the question. And the question for that high material removal rate, or for something that we need to reduce the time factor in, is profitability. I think at the end of the day, it all equates to the RPM that he spoke about, rupee per minute. And that is a very essential takeaway for all of us here today, because ultimately all these technologies, all these processes are a factor of that single unit, which is cost. Reduce cost, increase profitability. But what makes high-speed machining unique is that any process that has the ability to achieve the goal without reducing the quality or precision expectation of the end user is what becomes a cornerstone of that technology. And it is therefore we see that high-speed machining now has become the cornerstone of discrete manufacturing at the very least. When we speak of machining specifically, we can subdivide it into two broad categories. One, we can call it production machining, where the parts are typical, the parts are similar, prismatic in nature. You program those parts, and once you transfer it either to an SPM or a CNC machine, they run probably into hundreds of thousands or millions of components without requiring a change in the strategy in which those components are produced. And then when you look at the other side, which is typically about 15%, 85% of the machining market is about production machining. The remaining 15% is what we can classify into discrete manufacturing or discrete machining. Here, the components are complex. Each component varies in characteristics, material, in terms of the function that it needs to achieve. It differs from the previous. So there's a high variety, as we can call it. It's a high variety, high complex geometry, material. And when you want to address such components, often you will realize that the profitability in such products are a result of what you can save in the roughing phase. Also, what Mr. Menon rightly pointed out to. So the bulk of those operations are removing metal, the removing material from a chunk of block, or it could be a near net shape of that component again. So based on this, how the amount of time your cutting tool is in contact with the material is what defines high efficiency and high speed machining. And in order to address these challenges, there are certain core principles of high speed machining that we need to consider. Faster spindle speeds, again, a factor of cutting speed, as covered by Mr. Menon earlier. These faster spindle speeds allow for quicker material. So there's something called as a combination of the spindle speed and the feed rate. In cutting tool theory, there's a concept called as radial chip thinning. What radial chip thinning does is when you introduce a cutting tool into a material, it starts with a larger chunk when one tooth engages with the material as it starts shearing this material, and then when it comes out, you have a thicker edge and a thinner end. Um, and some of the earlier proponents of high-speed machining and these manufacturing scientists, they said that this is not a great quality. I think what we should try and do is maintain uniform chip thickness. And that's how the radial chip thinning concept came in. They started increasing feeds to make sure that the chip thickness starts becoming uniform. That presented another challenge because you could achieve that when you were doing a straight cut. But what happens when you introduce complex shapes, such as, if I can, these corners here, and these sudden changes in the toolpath direction? What happens here? That becomes a challenge. And therefore, there was a necessity to bring in strategies, CAM strategies, that could optimize toolpath cutting in areas that were not straight lines. One, the very simplest thing they did was convert all of the sharp corners into rounded corners, which meant that you would, of course, leave probably a pip at one edge because you're not cutting it through with an edge. But that could be taken through another straight pass, which was again controlled by the toolpath strategy. And therefore, these optimized toolpaths were a result of that. And in order to do so, you also required that the tool travel faster, which is higher feed rate, higher RPM. And then obviously you needed advanced materials, which is what the CBN, PCBN, CDN technologies that were adopted, high and specific coatings for solid carbides, which were then able to achieve these functions. And once you're able to achieve the first three, then ultimately, where are you going to conduct these processes? Obviously on the CNC machine tool. And therefore, along with the CNC machine tool, you came up with the work holding setup, rigidity of the work holding setup, then the cooling media, whether it was cutting oils, whether it was compressed air, whether it is a host of other cooling media that could be utilized in such cases, all of that. And alongside of that, the stability of your spindle, the runout of your spindle, the bearings of the spindle, to make sure that when you're performing such a high speed and high feed cutting, that your spindle also, the maintenance is absolutely reduced, which was again covered by Mr. Magesh when he spoke about reliability of machine tools. So all these factors became the core principles of high speed machining. And then come about the innovations. Now, multi-fluted carbide tools, specialized coatings, precision inserts, shrink fit technology, which was introduced some, I think, 20, 30 years back, moved away from the collet-based holding in order to support high-speed machining. Then the high-speed spindles with ceramic bearings, the hybrid bearing systems of the axes, the X and Y travel beds, thermal stabilization that was introduced into the machine tool with the design of the at the casting level itself. Machine tool companies started getting involved into FEA and FEM to understand how specific loads, when they are transferred onto the spindle, how can those be dissipated? All of that came into the innovations in machine tools. Specifically from the software, CAM software point of view, there have been a number of technologies that are part of the high-speed machining process. So we spoke about one of the technologies is dynamic machine tool technology, which is patented by Mastercam. Similarly, there are other CAM software that have a similar, strategies towards high-speed machining, and each of them specifically looks at one or two different scenarios. So when you specifically look at solid carbides, the proven method there is to have a low AE, which is step over, which is probably about 0.07 to 0.15 of your cutting tool diameter. That is your tool engagement. And then your cutting depth of cut is up to twice or three times the tool diameter size. And then the feed rates can be a function of the material and the machine tool limits that are available there. When all of these are put into the CAM software, the CAM software's brilliance until current generation has been the speed at which it computes these tool paths. And therefore, after all of these technologies are put in place, are the areas is machining in which you could then use these optimized strategies to reduce your costs. This is until now. Let's see a video here. And I put this video up specifically for one important aspect. When you start seeing these fireworks here, each of these holes, you'll see that that's an optimal high-speed machining in action, because all the heat that is being produced there is being carried away by the chips. And Mr. Menon mentioned that, the chips are a waste byproduct. And when you do that, you're able to, make sure that the work is not hardened, your tool life increases. And then because the chips are anyway going to get thrown away, all the heat is transferred to it. Way to embrace the future of machining and to optimize high-speed machining would be, again, continuous innovation. Training is more important, because as technologies start evolving, I started speaking about high-speed machining in the year 2003 and 2004. That is when we started talking about how companies need to adopt high-speed machining. That's a technology of the past. It needs evolved beyond that now. And I think training is one of the key components in advanced manufacturing techniques that will help company collaborate with partners across the machine tool, the cutting tool, the cooling media, the work holding devices. All of these people need to work harmoniously, and that will bring about sustainable practices going forward. Thank you for your patient listening.